Good morning, dear students. As in previous class, we have studied about heat exchanger, types of heat exchanger, and fouling factor we have studied. So after that, we are going for analysis of the heat exchanger. So in any part or in any machine, at any of the equipment, if you are developing this, you need to study about the design parameters of that particular machine and analyze at what extent that will perform its work, whatever the work you are assigning, how it will perform, that we need to analyze. So here also, a heat exchanger is also a device or the equipment, or it is a some attachment that is used to reduce the heat transfer or used to increase the rate of heat loss. Now here, analysis of the heat exchanger. In this, there are two methods for analyzing the heat exchanger. First one is the logarithmic mean temperature difference, the first one. After that, second one is the effectiveness NTU method. The NTU means number of transfer units. So these are the two methods. Logarithmic mean temperature difference. It means here the temperature is a function of logarithm of, it's a log of that temperatures. What are the temperatures of the fluid, that is hot fluid and the cold fluid. Now analysis of heat exchanger mainly include rating and sizing. The two methods are applied for analyzing heat exchanger. They are logarithmic mean temperature difference method, and second one is the effectiveness NTU method. The first one, logarithmic mean temperature difference method, that is also called LMTD method. So in the exam, compulsory he will ask one question on derivation, that is LMTD for parallel flow or counter flow, or he may ask NTU for parallel flow or counter flow. Out of these four, compulsory he will ask one for 8 marks. Okay. Now, the logarithmic temperature difference. So the thermal analysis of heat exchanger depends on variables like inlet and outlet fluid temperature, overall heat transfer coefficient, total surface of area of the heat exchanger, and the heat transfer rate. So on these conditions or these parameters, the rate of heat transfer is depending. The temperature difference between hot and cold fluid we are given as delta T. In some cases, he will take it as theta. Theta is equal to TH minus TC, means hot fluid minus cold fluid, temperature of the hot fluid and cold fluid, difference in temperatures of the hot and the cold fluids. In heat exchanger, we are studying only hot and cold fluids. Okay. Now delta T is varying with position along the length of the heat exchanger. The heat transfer becomes the whatever the heat transfer taking place in the heat exchanger, that is by convection only. So for the convection, the rate of heat transfer Q is equal to Q H AS into delta T you are having, but here I am using U AS into delta TM. U is the overall heat transfer coefficient, where H is the heat transfer coefficient for the convection. But here U is the overall heat transfer coefficient for the entire surface. There may be a conduction, convection, whatever that may take place. Okay, you know the value of U. Okay, and AS is the area, surface area, delta TM is the mean temperature difference across the heat exchanger. For heat exchanger, this mean temperature difference will be in the form of logarithmic ratio. So for any of the heat exchanger, if you are going to study, the temperature difference will be in the form of logarithmic relation. So that's why he has given the name logarithmic mean temperature difference, that we are calling as LMTD. So for analyzing or to calculate the formulas or to know the formulas or to derive the derivation, we should assume some points. First one, overall heat transfer coefficient is uniform throughout the heat exchanger. That is, U should be uniform throughout the heat exchanger. Specific heats and mass flow rates of both the fluids are constant. Specific heat and mass flow rate are constant for both the fluids. Both the fluids means hot fluid and cold fluid. Third one, potential kinetic energy exchanges are negligible. We are not going to consider about the energies that are developed inside the fluid. Due to motion of the fluid, there may be a kinetic energy. Potential energy also occurs. So we are not going for potential and kinetic energies. Fourth one, the heat exchange takes place only between two fluids. This is common term. Only between two fluids only heat exchange taking place, hot and the cold fluid. And the fifth one, temperature of both the fluids are constant over the given cross section. So it means if I consider it is a heat exchanger, if I want to measure the temperature here, the whatever the temperature, that is the temperature of both the fluids at a constant are constant or the given constant. If I want to measure the temperature here, the temperature of the hot and cold fluid should be constant. Like that we are assuming and we are deriving the equation. Now we are going for equation for deriving the equation for parallel flow heat exchanger. First one, analysis of the parallel flow heat exchanger. So before deriving any of the equation, first you should know what is parallel flow and what is the counter flow. Parallel flow means there is a fluids, those hot and cold fluids are moving in the same direction. At the same time, heat exchange taking place between hot fluid and the cold fluid. That we are calling as a parallel flow heat exchange. So see here, here there is a cold fluid that is entering towards this side. Again, there is a hot fluid. Both are moving in the same direction. The hot fluid continuously flows in the middle pipe. The cold fluid flows around the this surface. So like, when it is moving around the surface of the hot fluid, then it will absorb the heat from the hot fluid. Then cold fluid also, temperature of the cold fluid also increases. So now see here, here hot temperature is at higher temperature at the starting of this point. At the same time, the cold temperature, the temperature of the cold fluid is less as compared to this one. Now see here, it is a first line on the upper line, that is temperature of the hot fluid, and the lower line is the temperature of the cold fluid. Now see here, initially hot fluid temperature is at higher temperature, so that's why he has taken THI, that is temperature of the hot fluid at the inlet. I indicates inlet, and O indicates outlet. Okay. Now THI means temperature of the hot fluid at the inlet, and TH naught, temperature of the hot fluid at the outlet. Now see here, from the starting, when the here hot fluid enters into the pipe, after entering, the cold fluid absorbs the heat from this hot fluid. Then when it moves out of the this pipe, then heat will be, the temperature will be reduced. So that's why see here, this line will be in a decreasing manner. Okay, THI is at a higher temperature, TH naught is at a lower temperature. At the same time, cold fluid also entering at the inlet. When it enters at the inlet, that is having lower temperature. Cold fluid enters the lower temperature. So it is at the lower temperature. When it passes out of the that pipe or that container, then it will observe. It is having some. It has gained some temperature. So that's why temperature of the cold fluid is increasing at the outlet. Now see here. TCI is at lower temperature and TC naught is at the higher temperature. Now, what I will do, the difference between THI and TCI, that is theta 1. Before that, I have taken delta T, is the TH minus TC. So instead of writing delta T, he is writing theta. Theta is equal to TH minus TC. Theta 1 he has taken for inlet, THI minus TCI. Theta 2 is TH naught minus TC naught. That is hot fluid minus cold fluid. Whichever the temperature is higher, that one you have to take first. Now, when I consider some part of this heat exchanger, now see here, this is the length of the heat exchanger. When it flows from starting point to end point, I will be considering some part of that one. Why am I considering part of that one? The thickness should be dx, and the temperature, that is hot fluid, and difference in hot fluid temperature is dth, and difference in cold fluid is dtc. Okay. Now here he has written the same things. THI, inlet temperature of the hot fluid, TH naught, outlet temperature of the hot fluid, TCI, inlet temperature of the cold fluid, TC naught, outlet temperature of the cold fluid. CPH and CPC are specific heats of the hot and cold fluids respectively. MH and MC, mass flow rate of the hot fluid, mass flow rate of the cold fluid respectively. AS, surface area of the heat exchanger. Now I have taken here theta 1 is equal to THI minus TCI, theta 2 is equal to TH naught minus TC naught. Okay. After that, I'll write the equation for the heat transfer. That is total heat transfer between two fluids. The whatever the heat transfer taking place between those two fluids. That is Q is equal to MH CPH into THI minus TH naught. That is equal to MC CPC TC naught minus TCI. Now see here. MX CPH. So this is the standard equation we have studied while deriving the enthalpy equations in the BTD. Okay, that is Q is equal to MH CPH into Thi minus Th, difference in the temperature. Okay, difference in temperature I can write Thi. So see here in this figure, Thi is at the higher temperature, that's why I has taken Thi minus Tci. Okay, now MC CPC into Tc naught, outlet temperature of the cold fluid is maximum as compared to inlet temperature of the cold fluid. Now I can write the mass flow, as we have assumed mass flow rates are constant, MH CPH will be same. So I can write, now see here, Q is equal to, he is writing MS CPH into CH only and MC CPC into CC only. Okay, instead of writing those two terms, he has taken CH and CC. So Q is equal to CH Thi minus Th naught, that is equal to Cc Tc naught minus Tci, where Ch is equal to MSCPH, Cc is equal to MCCPC, are called capacity, heat capacity rates for the hot and cold fluids. So in some question he will give specific heat of the hot fluid and specific heat of the cold fluid, mass flow rate of the hot fluid and mass flow rate of the cold fluid. But and some other problem he may give heat capacity rates for the hot fluid, that is Ch. Heat capacity rates for the cold fluid is Cc. Those values he will give. You directly you have to substitute. Ch is equal to MSCPH. Whether you are getting MSCPH, you have to substitute that one. Now consider a small element of thickness dx. When I consider the small element of length dx, thickness dx as shown in figure for the hot fluid. First I am considering for the hot fluid. Now the rate of heat transfer from through that hot fluid dq. So D I am taking means I am considering strip of that heat exchanger or some part of that heat exchanger I am considering. So that's why I has taken dq. Okay, that is equals to minus MSCPH into delta TH. So negative sign he has taken because along the length of the heat exchanger, heat will be and temperature will be decreasing. So that's why he has taken negative along the length. That is dq is equal to minus MSCPH into delta TH. So I may write MSCPH as CH only directly minus CH into DTH. So DTH is equal to DQ divided minus DQ divided by CH. For the cold fluid similarly same, but that is negative sign is not there. Now for the cold fluid DQ is equal to MH MC CPC, it should be MC. Okay, you have to make change MC CPC into DTC. That I can write CC into DTC. So DTC is equal to DQ divided by CC. But for the element, total for total element, the temperature difference theta is equal to TH minus TC. Now differentiating this equation, d theta is equal to dth minus dtc. So substitute the value of dth as we have derived here, dth value. dth is equal to minus dq divided by ch, that you have to substitute. And dtc is equal to dq divided by cc. Taking negative sign common term and dq is the common term outside, d theta minus of dq into 1 by ch plus 1 by cc. So I can write dq, the heat flow rate for the element. So I can write UdA into theta. Why I am taking UdA into theta means U is the overall heat transfer coefficient, dA is the area for the element, and theta is the Th minus Tc for that element. So that's why I have to take that one. Now, after substituting dq value, now rearranging the equation, d theta by theta is equals to minus u into dA into 1 by ch plus 1 by cc. Now integrating on both sides. So here integration of d theta by theta is equal to minus is u is the, this is a common term, constant term u, because overall heat transfer coefficient, that is constant for entire element, 1 by ch plus 1 by cc, this is also constant. Only the variable is the area. So integration of 0 to ax into dA. Now integration of 1 by theta, you may get log theta. Okay, so integration from 1 to 2 you are having. So theta 1 minus theta 2 I can write theta 2 minus theta 1 I can write theta 2 by theta 1. Log base e theta 2 by theta 1 is equal to minus u as. As why I am taken means 0 to as. That is as minus 0. So as you will get 1 by ch plus 1 by cc. Now after doing that, now see here, I think you people might be in confusion this one. So integration now 1 by theta is the log theta. So limits are from 1 to 2. So upper limit minus lower limit theta 2 minus theta 1 you will get log theta 2 minus log theta 1 you may write log theta 2 by theta 1 minus u into as minus 0. I have to write here integration is from 0 to as. One time integration of x a is the dA is the a. So as minus 0. So similarly, you have to substitute the value. Log theta 2 by theta 1 is equal to minus uas into. So you will know that ch is equal to q by thi minus th naught. Cc is equal to q divided by tc naught minus tci as we have derived in the upper side. So now here, now you can see here. Here we have derived initially. So these equations. So see here, I can write here q ch is q is equal to ch into thi minus th naught. So q divided by thi minus tc naught is the ch. Where are you having ch? Q divided by thi minus th naught you have to substitute. Okay, see here. Q ch is equal to q divided by ch naught th naught minus tc naught you have to substitute. Now you substitute the values here. 1 divided by ch is there. Ch value is this one, and cc value is this one. You have to substitute those values. Now rearrange the equations. So in denominator it will be going for the numerator. 1 by q you have to take as a common term minus uas divided by q. So th naught thi minus th naught plus of tc naught minus tci. So I can write here inlet temperatures one side, outlet temperatures one side. Now temperature of the hot fluid and temperature of the cold fluid, Thi minus Tci, I can write theta 1. Thi minus Tci is theta 1. Th naught minus Tc naught is the theta 2. Here negative sign I have taken common term because I need to write Th naught first. So that is theta 2. Now, so log theta 2 by theta 1 is equal to minus Us divided by Q into theta 1 minus theta 2. So taking common term towards this side. So negative, if you take the negative sign this side, you may rearrange or you may send that negative sign inside. You may write theta 1 by theta 2. Log base E theta 1 by theta 2 is equals to UAS divided by Q into theta 1 minus theta 2. Now write the equation for the Q. Q is equal to UAS into theta 1 minus theta 2 divided by log base E theta 1 divided by theta 2. So this equation theta 1 minus theta 2 divided by log base E theta 1 by theta 2 we are writing as theta m, that is mean temperature difference. So Q is equal to UAS into theta m, where theta m, theta 1 minus theta 2 divided by log base E theta 1 divided by theta 2 is called logarithmic mean temperature difference. This is LMTD. So this is the LMTD derivation for the parallel flow heat exchanger. This equation will be same, Q equation. Q is equal to UAS into theta m will be same for both parallel flow and counter flow. But the thing is theta m value will be changing. Okay. Now this is counter flow heat exchanger. In the counter flow heat exchanger, the fluids hot and cold fluid are moving in opposite direction. When they are moving in opposite direction, the temperatures will be changing. Okay. Now see here. You can see this is a arrangement for counter flow heat exchanger. In this arrangement, hot fluid is moving inside the pipe, cold fluid enters here and exits here. Now, similarly, I'll be writing the temperature distribution curve. How the temperature distribution in the counter flow. First one, hot fluid is entering into the pipe. When that enters into a pipe, heat is to be reduced. It means temperature falls from higher temperature to lower temperature. So temperature. Now here the temperature is at a higher temperature. So here the temperature is at the lower temperature because heat reduces from higher temperature to lower temperature. After that, for the cold fluid that is moving in opposite direction, at the entry, of the hot fluid, the cold fluid also has increased some temperature. So that's why Tc naught is the higher temperature and Tc naught is the lower temperature. Or Tci is at lower temperature. When it goes inside the pipe, then it will observe the temperature and it reaches to some value. Okay. Now, are you considering element dx? dTh is equal to dTh here, that is temperature difference in hot fluid, temperature difference in the cold fluid. Now, theta 1 value, only theta 1 and theta 2 value will be changing. In the previous case, theta 1 value Thi minus Tci, theta 2 value Tci minus Tc naught. Now see here in the upper side, Tc naught minus Tci, that is not Tci minus Tc naught. So see here, Thi minus Tci theta 1, Th naught minus Tc naught is the theta 2. Now here in this case, theta 1 is equal to Thi minus Tc naught, theta 2 is equal to Th naught minus Tci. Okay, this is the difference in theta 1 and theta 2. Remaining will be same as it is. Now writing same terms. Now here also you will write Q is equal to MSCPH is equal to MCCPC. Thi minus Th naught, this is temperature hot fluid and this is for the cold fluid. Okay. Now MSCPS CH, MCCPC CC, theta 1 Thi minus Tc naught here. In previous case Thi minus Tci, but in this case Thi minus Tc naught, theta 2 Th naught minus Tci. For a small element, area dA, heat transfer can be done, dq is equal to MSCPH dTh. So minus Ch dTh, negative sign, that is along the length of the heat exchanger, temperature will be reducing. So that's why we are considering negative sign. Now dq MSCPS MCCPC for hot fluid and cold fluid he is writing for an element. Now write dH is equal to minus dq divided by ch, dTc is equal to minus dq divided by cc. Now theta is equal to Th minus Tc, we know theta is equal to dTh minus dTc. Substitute the value dTh and dTc, dTh and dTc we have to substitute, minus dq common term 1 by ch minus 1 by cc. Now d theta is equal to minus u dA theta into 1 by ch minus 1 by cc is the value you are getting. Now see here the value, that is minus cc dTc he has taken, because here also the temperature will be reducing along the length, but in the previous case he has written only cc dTc. You can see here. Now see here, cc dTc only he has written, but in this case minus cc dTc, that is temperature is moving in opposite direction, heat flowing in opposite direction, that's why he has taken minus cc dTc. That you should remember. Only here is the variation. Okay, here minus into minus plus, here taken minus dq is a common term, 1 by ch minus 1 by cc, d theta minus u dA theta into 1 by ch minus 1 by cc, d theta by theta is equal to minus u into 1 by ch minus 1 by cc into dA. Integrating between the limits, integrate and apply the limits, you will get log by c theta 2 by theta 1 is equal to minus us into 1 by ch minus 1 by cc. So after that, rearrange the term, 1 by ch and 1 by cc value have to substitute there. Ch value is q by thi minus th naught, cc value q divided by tc naught minus tci. Now rearranging the term of q, you have to take on the outer side. Now after that, whatever the things we have written here, it is minus uas divided by q into thi minus th naught minus tc naught minus tci. So rearranging the term again, minus uas by q thi minus tc naught minus th naught minus tci. So thi minus tc naught is the theta 1, th naught minus tci is the theta 2 for counter flow. For counter flow, parallel flow THI minus TCI, theta 1 is equal to THI minus TCI. काउंटर फ्लो के लिए theta 1 is equal to THI minus TC0. Theta 2 TH0 minus TCI for counter flow. Now you substitute those values, minus UAS you have to write here. Send that negative sign, you can write log base E, theta 1 by theta 2 is equal to UAS divided by Q into theta 1 minus theta 2. Now Q is equal to UAS into theta 1 minus theta 2 divided by log base E, theta 1 by theta 2. That is UAS into theta M. Theta M is called LMTD for, and there is logarithmic mean temperature difference. Now, after that, both equations are same, but the thing is, the theta 1 and theta 2 value will be changing. For parallel flow is different, for counter flow is different. For parallel flow, theta 1 is equal to THI minus TCI, theta 2 is equal to TH0 minus TC0 for parallel flow. For counter flow, theta 1 is equal to THI minus TC0. Theta 2 is equal to TH0 minus TCI. Okay, these terms you have to remember. Now capacity rates is the product of mass flow rate and the specific heat of the fluid at constant pressure. Cc is equal to mc cpc, ch is equal to ms cph. Capacity ratio, the ratio of this term, it is defined the ratio of minimum to maximum capacity rate, that is ch by cc or cc by ch. Whichever is the maximum you have to take in the numerator, whichever is the minimum to take in the denominator. C is equal to ch by cc if cc is less than ch, or c is equal to ch by cc if ch is less than cc. Now after that we are going for effectiveness of the heat exchanger. So effectiveness of the heat exchanger, it is the ratio of energy actually transferred to the maximum theoretical energy transferred. It means actually what it is transferred and theoretically what it should transfer. That ratio we are calling as effectiveness. That is effectiveness is equal to Q actual by maximum. So Q actual is MSCPH into THI minus TH0 for hot fluid, for cold fluid, MCCPC TC0 minus TCI. Maximum available temperature difference THI minus TCI. That is C maximum possible transferable occurs when the fluids of a small heat capacity rate undergoes maximum temperature difference. That is Q maximum is equal to C minimum into THI minus TCI. These values, these equations you should remember. Effectiveness is equal to Q actual by Q maximum. Actual is MSCPH into THI minus TH0 or MCCPH into TC0 minus TCI. Q maximum is equal to C minimum into THI minus TCI. So the ratio, if you take the ratio, whatever the ratio you are getting, that is called effectiveness. Now effectiveness is equal to, you take that ratio for the hot and cold fluid is same. Okay. Now like that, you need to derive the equations. So effectiveness is equal to, if CH is less than CC, then effectiveness is equal to THI minus TH0 divided by THI minus TCI. When CC is less than CH, TC0 minus TC0 minus TCI divided by THI minus TCI. Now these are all the values, these are all the formulas are available in the data handbook. Okay. So you go through the data handbook, you may use Hegde or this Kodandrama data handbook and refer those data handbooks and get the values. Now in the next class, we will go for number of transfer units, that is NTU method for calculating the sizing of the rating or sizing of the heat exchanger. It is the measure of size of the heat exchanger. It is a dimensionless parameter. There is no need for the NTU. Okay. NTU is equal to UAS divided by C minimum. This is the equation. So for parallel flow, what is the NTU, and for counter flow, what is the NTU? We will study in the next class. So before that, importance of the NTU effectiveness method. What is the importance? So in the exam, he may ask, what is the importance of give the definition of NTU, or what do you mean by NTU, and what is the importance of NTU, he will ask. So NTU, the analysis of heat exchanger mainly involves rating and sizing. The rating problems mainly deals with the determination of heat transfer. the fluid outlet temperature for the already sized heat exchanger. This is for rating of the heat exchanger. The sizing problem deals with the determination of metric dimensions to meet the specified heat transfer requirements. If the inlet and outlet temperatures of the hot and cold fluids and overall heat transfer coefficient are known, LMTD method is used to solve the both rating and sizing. However, if heat transfer coefficient is unknown, then determination of rating and sizing by LMTD is very difficult. It is overcome by NTU method. If I don't know overall heat transfer, it is not possible to calculate the values by using LMTD method. Now I need to go for NTU method. Okay. In next class, we will study about this NTU method. Okay. Now this is we conclude here only.